Okay, so this module will be one where we focus on electromagnetic radiation and electromagnetic spectrum, but there are a few things we need to do before we get to that point. We need to discuss waves. You've probably discussed waves way back in elementary school. For some of you, that wasn't that long ago, but I know it's not something that you necessarily have talked about a lot, even through high school. So we want to look at waves. We want to look at like the vocabulary related to waves and how we measure waves and the types of waves. I will actually add some extra videos with animations so that you can see the different motions and so forth, but difference between transverse and longitudinal waves. And then we're going to get into a video or a lecture on how light is produced, like basically why is red light red, why is blue light blue, why are X-rays X-rays. So we'll get into that, and then we'll really get into the nuts and bolts of the electromagnetic spectrum, which some of you, actually all of you, live in. I'll probably offend some of you in some of these videos. So it's some of you cannot survive without the electromagnetic spectrum. I'll just put it that way. Ignoring the visible light part, but of some of the other parts. And so we'll talk about those, and we'll really break down the electromagnetic spectrum. Don't memorize. Really understand how the electromagnetic spectrum works. You need to know the different components in order, but you really need to know like what size high energy, what size low energy. Sorry, I'm jumping ahead. I apologize. You really need to be able to digest and dissect the electromagnetic spectrum. So what are waves? So if I ask you to draw a wave on a piece of paper, probably 90% of you would draw something that looks like that right there. And so let's look at parts. Most of us would know that this is the crest, this is the trough, and if we put it in equilibrium, then this height here is the amplitude. So these are the physical components. And if we do some measurements, so if we go from crest to crest, or trough to trough, this is the wavelength, and we use the Greek letter lambda to measure wavelength. So like this would be wavelength as well. So one complete wave. So you want to go through and look at the components. Now what I have pictured here and what most of you would sketch is a transverse wave. So the wave, this is the motion of the wave, but the particles actually go up and down. So like in a water wave, the wave is moving to the right, but the water molecules actually only move up and down, except right at the coast on the beach. So if you're out in the ocean, the waves actually only, think about it, your boat only goes kind of up and down. It's not moving necessarily horizontal unless you're in a current. So transverse waves look like a sine wave, like a water wave. So that's a great example of a transverse wave. Other examples of a transverse wave are the electromagnetic waves. Or radiation. I'll call them waves. I won't call them radiation. I'll call them rays. I'll call it light. They're all the same thing. And if you're familiar with earthquakes, the S wave. So the earthquake produces P waves and S waves. S waves are actually transverse waves as well, where it oscillates up and down. That's where you get that kind of that up and down motion for an earthquake. Now the other type of wave, see if I can spell this correctly. That's not even close. Let me fix this. I always misspell that word. I don't know why. Longitudinal, just like it sounds. I want to put that extra N in there because I think I say it that way. Longitudinal waves. So this would be like a slinky. So you have these like this coils here, and you compress it. So the wave goes this way and this way, and the particles go, so the waves oscillate back and forth. So you want to compress the wave, like you would see here. And again, these animations. So you compress it here, and then when you're looking at it a little bit later, it's here, and then it's here. So you can see the wave moving to the right, and the particles are doing the same direction, so they're oscillating left and right as well. So longitudinal waves, the the motion of the wave and the particles are all going to be on the same plane. Sound is a great example of longitudinal waves. Ultrasound. So in one of the next modules, we'll talk about sound and really get into sound and ultrasound, and basically get into these longitudinal waves. And then remember I mentioned that earthquakes have P waves and S waves, the P waves for the earthquake. So earthquakes produce both types of waves, these longitudinal and these transverse waves. So let's go back and look at how we're going to look at some of these things. So we have these two different types of waves. The components are going to be the same. So we're looking at a wavelength type of deal. So if we're looking at this, a lot of times when we talk about a wave, we talk about the number of waves going by, or the frequency of the wave, or the rate of the wave. So the frequency of the wave, this is like the number of waves per second, can be calculated using the speed, where v is equal to the speed of the wave, and we get this equation, v is equal to wavelength times frequency. So if we're looking at units, we know from the past, so let's write this out so I can work underneath of it, v is equal to meters per second. Well, wavelength is a distance, so that's going to give us meters for units, and then we've got to figure out what this unit for frequency is. Well, if I divide everything by meters, these meters cancel, I'm left with 1/seconds. So my unit for frequency is equal to 1/seconds, or seconds inverse, or hertz is a common way of writing as well. They're all the same thing. So if you have 10 hertz, it's 10 waves per second, or 10 inverse second, or 10 1/seconds. You can write it all the same. It's going to be the same scenario there. So we have this equation, and then a lot of times we like to determine what's the time for that wave to go by, and that's equal to the period, where t is equal to 1/f. So if you think about it, the greater the frequency, the shorter the time for the wave. So that's why I was going to go through. The greater the frequency, the shorter the time between the waves, and the smaller the frequency, the longer the time between the waves. So hopefully this gives you kind of a good review or introduction. Again, I'm going to post some videos up that have animations because you can see my drawings are kind of sad. And then we can go through, now we're going to go through and kind of break down in the next video how we get red light and how we get blue light, and we get the different components of the electromagnetic spectrum.